So good morning students. In previous class, we discussed about nice and ugly domains. In this class, we are going to discuss about domain testing. Okay. So this is the domain testing strategy. General domain testing strategy. The first step is select test points near the boundaries. So near the boundary. So what is a domain? So domain is nothing but it's a boundary. For example, so this is the boundary for a variable. So let us assume this is the domain for a variable. Here in domain testing strategy, the first step is you are going to select test points near the boundaries. That means you are going to test the points like here. If you observe that this is the point, the red color dot. Now, so these are the points you are going to select. Okay, that's the strategy. And second one, so define test strategy for each possible bug related to boundary. So these are the different bugs that is related to the boundary. And next one, test points for domain useful test. It's adjacent domain. So adjacent domain is nothing but, for example, so this is another domain. So this is another domain. So this is another domain. Now the test points for a domain useful to its adjacent domain. That means if you try to check a test point here. Now, so this test is useful for adjacent domain also. Okay. So next one, run tests by post-test analysis determines if any boundaries are faulty and if so, how. That means run the test and by post-test analysis determines if any boundaries are faulty and if so, how. Here you are running some test cases by post-test analysis. So what it means, after testing, you are going to analyze the why you get the bug. Now, if you find any boundaries are faulty, then you are going to find so how it's happened. So next one, run enough tests to verify every boundary of every domain. Okay, run enough tests to verify every boundary of the domain. So now you can observe these are the boundaries. Okay, so now, so for example, I am taking a variable x less than 10 and x greater than 0. Now in this, if you observe that, so what are the boundaries? The boundaries is nothing but 10, 0. So these two are the boundaries. Compulsory you are going to check so these two test cases. Okay, and so these are the different strategies you are going to follow for domain testing. Okay, the domain testing strategy is simple. The first one is domains are defined by their boundaries. Therefore, the domain testing concentrates test points or near boundaries on or near boundaries. So that is the first step. So second step, so classify what can wrong with boundaries, then define a test strategy for each case and pick enough points to test for all recognized kinds of boundary errors. So define test strategy for each possible bug related to boundary. Okay. So next one, so because every boundary serves at least two different domains. Test point used to check one domain can also be used to check adjacent domains. And so run the tests by post-test analysis to determine if any boundaries are faulty and if so, how. And finally, so run enough tests to verify every boundary of every domain. Okay. So these are the domain bugs, domain test for specific domain bugs. So generally, these are interior point, exterior point, epsilon neighborhood, extreme point, and on point. Okay, so we discuss one by one. The first one is interior point. Okay, so let us assume, so this is the domain. So this is the one domain. So this is another domain. In this, the interior point, here you are going to take one epsilon neighborhood. So that means, for example, this is the epsilon neighborhood. Okay. Now the interior points. So this is the interior point. Interior is nothing but inside. An interior point is a point in the domain such that all points within a arbitrary small distance are also in that means so small distance in the thing, but here you are going to compare the interior points with the help of this epsilon neighborhood. So if this is the distance, now so this is the interior point, simply saying what are the points are inside the boundary, so those we are called as a interior points. Okay, this is the interior point, and this red dot is epsilon neighborhood. So this is the epsilon neighborhood. And the boundary point, in this I hope you all are know the boundary points. So boundary point is nothing but, so this is the boundary point. So this is the boundary point. Now the boundary point is one such that with an epsilon neighborhood, they are points both the domain and not in the domain. So if you observe that, so this is the boundary point, so half in the one domain, another half in the another domain. Okay, so that is a boundary point. The boundary point is one such that, so within an epsilon neighborhood, so that means this is the epsilon neighborhood, or points both in the domain and not in the domain, half in the domain and half in not in the domain. Okay, so next one, the extreme point. Extreme point, so this is the extreme point. This is the extreme point. An extreme point is a point that does not lie between any two other arbitrary but distance between of domain. So now, if you observe, this is the extreme point. So now, so this is the half in another domain, and it is convex points of a convex domain. And no, this is the extreme domain. Extreme domain. Next one, an on point. Just wait. Okay. So next one is on point. So on point is on the boundaries. So these are the on points. If these points are the on boundary, so then we call those points as a on boundary. And next, off point. So off point is a point near the boundary but it in the adjacent domain. So here if you take the points like this, so these are the points. So near to this boundary, if you observe, this is the boundary. So these 2 points are near to this boundary, but in the adjacent domain. So these two are in the adjacent domain. Okay. If the boundary is open, an off point is a point near the boundary, but in the domain it's being tested. Okay, that means if the boundary is open, now, so this is the open, like this is the boundary is like this. So this is the open. An off point. So what is the off point? So off point is nothing but, so those are the near to the boundary, but in the adjacent here, if you like this. Now, so these point near to the boundary, so but in the domain being tested. Here also you are going to test the test cases for this point. Okay. And next one, so testing one-dimensional domains. Testing one-dimensional domains. So one dimension is nothing but, here we have only one. So this is the diagrammatic representation. So extreme point, boundary point, epsilon neighborhood. So this is the distance, and off point and on point. Okay. Now testing one-dimensional domains. Testing one-dimensional domains. Just wait. Okay. So bugs for one-dimensional domain to the open domain boundary. So these are the different types of bugs we are going to get. We are going to test when we are doing the domain testing. So domain boundary bugs. So one is 1D domains, 2D domains. Third one is equality and inequality predicates, random testing, and testing n-dimensional domains. Okay. The first one is testing 1D domains. So these are the bugs with open boundaries. So these are the bugs with open boundaries. Here, if you observe that this is the closure bug. So this is the X. It is closer to, so A and B. Okay. And shift left bug. Shift left bug is nothing but the bug is so shifted towards the B domain. So this is the X bug, and this is shift left bug. And similarly, shift right bug. So this is the X. Now this becomes X1. So that we are called as a shift right bug. And so bugs with open boundaries. So this is the missing boundary. So this is the missing boundary. The first. Wait. So this is the missing boundary. And this is extra boundary. Here if you observe that this is the C you got. So that is a extra boundary. And so bugs with closed boundaries also similar to these boundaries only. One is closure bug, another one is shift left bug and shift right bug, and missing boundary and extra boundary. Here, so for example, if you assume that the boundary was to be open for A, okay, the bug we are looking for the closure error which converts less than to, so less than or equals to, so less than to, less than or equals to, or greater than, maybe changed as a, so greater than or equals to. Okay. And next one, testing two-dimensional domains. So testing two-dimensional domains. In this also we have, so closure bug, so boundary shift up and down. So why here we have so two dimensions, means there are so two variables, and tilted boundary and extra boundary and missing boundary. Okay, we see one by one. The closure bug. So first one is so closure bug. So this is the closure bug. So this is the A. So this is so two dimension and like this. So this is the A and so this is the B. Let us assume. So this is the B. So now so this is the test point. So these two are the test points. Now so this we are called as a so closure bug. So it shows that so faulty closure such as so might be so caused by using wrong operator. So here so for example so x greater than or equals to k, but when we write so x less greater than k. Okay, the two on points detect this bug because so those values will get b rather than a processing. So what it, for example x greater than or equals to 10, we are going to check. So instead of this, if you are writing x greater than 10 only, so then this bug we are called as a so closure bug. Okay, the next one, so boundary shift up and down. I hope you all are understand. The boundary shift is nothing but now the test case is here. So boundary shift up. If it is in down means the boundary shift down here. Here the bug is shift up, which converts a part of domain B into A processing and denoted by A. So this result is caused by an incorrect constant in a predicate, such as so for example here I am taking x plus y greater than or equals to 17. X plus y greater than or equals to 17 when actually the x plus y is greater than or equals to 7. Our intention is I am going to check so x plus y so greater than or equals to 7. Instead of that I am checking here x plus y so greater than or equals to 17. Okay, so this off point so catches this bug. Okay, so this the shows a shift down that is caught by the two on point. And next one is so tilde boundary. So tilde boundary is nothing but so this is the so tilde boundary. A tilde boundary occurs when coefficients in the boundary inequalities are wrong. So for example, so this is the so 7x plus so 3y greater than 17 is our intention. Okay, so but we write like this, so 3x plus 7y greater than 17. Here the x and y values are changed. These two are the tilde. So actually you want to write 7x plus 3y so greater than 17. Instead of that I write 3x plus 7y greater than 17. So these values are tilde. So that we are called as a so tilted boundary. So tilted boundary and extra boundary. The next one is extra boundary. An extra boundary is created by an extra predicate. An extra boundary is created by an extra predicate. An extra boundary will slice through many different domains and will therefore cause so many test failures for the same bug. Okay, so for example, so f of a equals to f dash f dash f of a dash f of a dash, and instead of you are going to find a with a dash, you are going to find the function of b with function of b dash. Okay, now so this is the extra boundary. So why? So this is the fa equals to f of a dash. So this is enough for your program. In the same program, you are going to write the same functionality. Then that leads to extra boundary. So these two are the same. So, but here you are going to check for this b also. So this is extra boundary. Okay. Actually, these two values are the same, but you are defining this one more time. So this we are called as a extra boundary. Okay. So next one, missing boundary. So missing boundary, that means you are going to actually write f of a equals to f of a dash, but you miss this instruction or function. So that we are called as a missing boundary. A missing boundary is created by leaving a boundary predicate out. So extra boundary means a extra predicate. So a missing boundary is nothing but you are leaving a boundary predicate. A missing boundary will merge the different domains, and as the extra boundary will cause so many test failures. Okay, so this is about so testing so 2D dimensions. So testing 2D dimensions. Just wait. Okay, so these are the domain share tests and so 2n and 3n. So domain share test what we discussed up to now. So closure bug, so boundary shift or up down, till boundary, all these things. So next coming to so third one. So third one is equality and inequality predicates. Equality and inequality predicates. An equality predicate defines a line in 2D. So what it means? Every predicate such as, so for example, the predicate so x plus y equals to 17. So define so lower dimensional domains. So for example, if there are two input variables, a two-dimensional space, an equality predicate defines a line, a one-dimensional domain, so that is the x. Similarly, an equality predicate in so three dimension defines a planar domain. Okay, so an equality predicate defines a line in 2D. Why? Here we have so two variables. So you are going to predicate, sorry. So an equality predicate defines a line in so 2D. So that means this is the one and this is another one. Okay, if you observe that this is the test cases, so these are the so bugs. To avoid bugs, you are going to so predicates an equality predicate defines a line in 2D. Here, if you observe that this is the equals to check, we are going to x plus y equals to 17. Now you can check that the value of the x only equals to 17. So for example, if I am writing like this, so x plus y so less than 17 and greater than 1. Now we have the boundary. But inequality and inequality predicates, you are going to check exact value, x plus y equals to 7 or x plus y not equals to 7. In both the cases, you are going to check only one value. Okay, so that means, so this is the an equality predicate. You are going to draw the line. So this is the line. So for example, so this is the 17. You check this. If we get the value here, then that is a bug. So that is a bug. Okay, so next one, random testing. So next one is random testing. Here, a point in the center verifies computation. So random testing is nothing but, so this is the point in the center. You are going to take for domain testing, and so corresponding cases for experience shows programmer have. So these you are going to you are going to find the trouble. So now here, what is the probability that a set of random chosen test points will meet the criteria? Here you are taking some criteria. For example, this is the domain. If you observe that this is the domain. Now, so randomly you are going to check all the test points. So this is the center, and these are the test points you are going to check. So all these are the extreme point. So this is the boundary points. So these are the inner point. Okay, so these are the extreme. Now, so random testing is nothing but, so randomly you are going to test all the as much as possible test cases. Okay, and next one, testing n-dimensional domains. So testing n-dimensional domains. Here, so one dimension means there is only one variable. So two dimension means so two variables. N dimensions means n variables. So we get here. So for domains, define our n dimension input space with p boundary segments. Boundary segments. The domain testing strategy, so generalized to require at most n plus 1 p test points. So if you have n dimensions and p boundary segments, then so you are going to require at most n plus 1 into p test cases. Okay, so n on points and 1 off point. Okay, I hope you all know. So it is on point and off point. And extreme point shared. Here, so 2 into p points. So extreme points, you are going to do the domain testing, that is 2 into p points. And next one, equalities over m dimensions create a subspace of n minus m dimensions. So orthogonal domains, the consistent boundary, so closures, so orthogonal to the axis and complete boundaries. So this is independent testing. So here, so the domain testing is nothing but you are going to do the white box testing. So domain testing is nothing but it is a white box testing. Now, so these are the strategies you are going to follow. So when you are doing the domain test for your program. Okay, here, so this is the extreme point. Extreme point. So when the extreme point sharing is possible, the number of points required per domain can be little as 2p per domain. So domain boundaries which are orthogonal, so which are orthogonal to the coordinate axis have consistent closure and extend over the entire number space can be tested independently for other boundaries. So equality predicates define over m dimensions, that is m less than n. So create a subspace of n minus m dimensions. Okay, so this is about domain test strategies, domain testing. In so tomorrow class we are going to discuss about the procedure. So procedure for domain testing we discuss in tomorrow class. So thank you all.